In this video, we are going to talk about voltaic cells, which are also known as batteries. So this is a very basic drawing of a battery. They don't really look like this. I can explain more in class as far as what batteries look like. We know them as the little round cylinders or maybe the little squares with the two prongs, but what's going on the inside is some version of this, no matter what the shape of the battery. They all pretty much work the same. The parts maybe have a different shape or a different look, but it's all pretty much the same stuff. So batteries are composed of two electrodes. So this is an electrode over here, and this is the electrode over here. And they are just pieces of metal. It could be a chunk of metal, it could be a sheet of metal, it doesn't really matter. It could be a coin for all that matters. Like a penny could be the electrode, or a quarter, or something like that. All right, this would be just a voltmeter. It doesn't necessarily, this would be just if you were measuring like how much power your battery gives out, but this would also be where your electronic device goes. So this would be the thing that you're powering, okay? We have this thing in the middle that is actually called the salt bridge. I'll explain what that does in a second. And then we have two half cells, half cell 1 and half cell 2, and they are typically filled with a solution. So I'll draw my little bit of a water line there. That's the solution, okay? And so they're filled with water and some salt, all right? So now, let's start figuring out how batteries work. There are some steps down here. So step 1 is that the electrons flow through the wire. This is our wire. They flow through the wire, and they flow on table J from high to low. So if we look at the two metals, Ag and Sn, and we go to table J, we say, all right, which one is higher? Sn is higher than Ag, so the electrons are going to flow from Sn to Ag. That means that in this example, they are going to flow to the right. Now, they don't always flow to the right. I could take these two electrodes and flip them, and then they'd flow to the left. So don't just assume it's one direction. It's always from high to low on table J. Now, there's another saying. They also flow from anode to cathode, okay? So they flow from anode to cathode. So that means that Sn, the name of the Sn electrode is the anode, and the name of the Ag electrode is called the cathode. Next, they also, we have our Leo and Ger, Leo goes Ger, we know that saying, lose electrons, oxidation, gain electrons, reduction. So now think about this. Since the electrons are flowing from Sn to Ag, they are leaving Sn, and they are going to Ag. Ag is going to be where your gain electrons reduction happens, and your Sn is where your lose electrons oxidation is going to be happening. We have another saying at the very bottom, and it's that Leo, the lion, goes Ger, we know that. And then there's another one, the anox and the red cat. Here's what it means. The anode, that's the an and anox, is where oxidation happens. So anode, oxidation. So as soon as I named this the anode, I actually already knew that this is where oxidation happens. And therefore, the cathode is where reduction happens. So you could have figured it out using Leo goes Ger, but we're also going to throw in the anox and the red cat. Now, the next part of the saying, the anorexic ox gets thin, okay, pardon the phrase, but it works for this example. And then the red cat gets fat, okay? And I'll explain what they mean when we actually get to that part. So the first thing we need to know is that the electrons flow from Sn to Ag, from anode to cathode, and that's where the anox and the red cat are. Okay, so that's how you know those. And then the next part of the saying is the anorexic ox gets thin and the red cat gets fat. And what that refers to is the mass of the electrodes. So the Ag electrode is going to get fat. It's going to gain mass. We'll explain how in a minute. And the Sn electrode is going to lose mass. It's going to get thin or skinny or whatever you say. Okay, so next part. In the half cells, here are the two salts that are in the half cells. Now, I said the half cells have water in them, but I said specifically a solution. What makes it a solution is it has a salt dissolved in it. So when you take SnCl2, that's a salt, and you put it in water, it is going to dissolve and dissociate into Sn plus 2 with an AQ sign and 2 Cl minuses, also with an AQ sign. AgCl, when it goes into water, it breaks up into Ag plus 1, aqueous. We've done this a bunch of times. You should know how to do it. Now, here's where the saying comes in, which one gets fat and which one gets skinny. The electrodes, when they are in their bar, so these are bars of metal, that means they are in the elemental form. Their oxidation states are 0 because all elements have an oxidation state of 0. These guys are in compounds. Now, granted, the compound broke up, but that doesn't matter. They still are in compounds, or they were in compounds. That's why they have the oxidation states. So look at what happens. If Sn, 0, is the source of the electrons, think about this. If Sn loses an electron, what's its charge going to be? Well, it's going to go positive. In this case, the Sn loses 2, but that's not what's important. Take a look. This Sn, when it loses the electron, it becomes that Sn. So now think about this. If the Sns are losing electrons, they're becoming positive, they're dissolving into the water, what's going to happen to this electrode over time? Well, it's going to dissolve into the water and it's going to get really skinny, like if you were to take like an icicle as it's melting. It's going to get thinner and thinner and thinner. Eventually, it'll totally disappear. I just draw it like that to show that it's getting skinny. And that is where the saying, the anorexic ox gets thin or loses weight or mass, whatever you want to say. Now, those electrons go over here and they actually build up on this electrode. So now I've got these little negatives on this electrode. Now think about this for a second. I've got Ag plus in the water, and I've got negative electrons on the electrode. What do opposite charges do when they get next to each other? They attract. So the Ag pluses from this water or solution are going to actually go to the bar or the electrode, gain the electron, and end up becoming that electrode or that element, Ag0. So that's why this one over time, now think about it. If this electrode over time consistently has Ag atoms or Ag ions getting stuck to it and becoming Ag atoms, remember the atom and ion word mean different things, this electrode is going to gain mass over time. So it's actually going to get bigger and bigger and bigger. And it'll look something like that. Think of it like, I don't know, if you've ever made a candle, if you ever like gone to one of those like old-timey places where they have you dip the candle in the wax, and every time you dip the candle in the wax or the candle string, it gets a little fatter and a little fatter and a little fatter, and eventually it makes a bigger candle. Well, that's basically what's happening here. All right, so that's where the two sayings come from. The red cat gets fat, the anorexic ox gets thin. That will always be true, okay? Whichever one is the anode is always going to lose mass. Whichever one is the cathode is going to gain mass. Now, if this was all that your battery had, nothing would happen, all right? Because this would happen once or twice, and then your battery would lose power and it wouldn't actually work. Here is where the salt bridge comes in. The salt bridge prevents ion buildup. Now think about this for a second. If the SNs are becoming positive and jumping into the solution, what's going to happen to the amount of positives in this solution over time? Well, it's going to become more and more positive. Do two positives want to be next to each other? Well, of course not. So if the two, eventually what would happen is this solution would build up with positive charge, and then your SN atoms aren't going to want to go into your solution to become SN ions because they don't want to be more positives next to each other, and that would stop your battery from working. The same thing over here, where you were using up all the positives from the solution and making them stick to the battery. That's making the solution become more negative because that's what's left behind. Eventually, if the solution becomes too negative, then the ions aren't going to be attracted to the electrons anymore because the solution that they're in will be more negatively charged than the electrode itself. That will make your battery stop working. So what do? We allow the excess charge to go through the salt bridge. In other words, your SN ions here are going to travel through, this salt bridge is filled with solution or water or whatever, and the Cl minuses are going to go through here to attract. And basically, you get a buildup of positives here, you get a buildup of negatives here. The salt bridge allows them to come together and cancel out the buildup, which makes your battery keep functioning. So when we think of the salt bridge, here's what it does. It's called ion migration, or the words mean the same thing as far as we're concerned. It allows ions to go from one side of the other, which is what a bridge does. If you think about it, bridges allow people or cars to go from one side of land to another, crossing a body of water, right? And this is a bridge specifically for salt. And another word for salts when they dissolve in water is ions, hence the term salt bridge. It prevents charge buildup in the battery, okay? So that's what salt bridges do. Last but not least, we have to draw the two half reactions for this battery and we're done. But here's the good part. We actually already did it, or we did 2/3 of it. See how SN0 became this SN2 plus? Well, guess what? That is your oxidation half reaction. Take a look. SN0 turned into SN plus 2. Now that's most of it. We just need to figure out, well, we know it lost electrons because it's oxidation. So going from 0 to plus 2 means you lose 2 electrons. So I add 2 electrons to the right side. There's my half reaction. If you wanted to get fancy, you could add in the symbols. This one was a Q and this one was a bar, so it was a solid, but it's not really necessary. And then the other half reaction, well, guess what? We have it over here. We've got the Ag0 became the Ag plus 2. We already drew it out. So, or plus 1, sorry. Ag plus 1 electron becomes Ag0. That was the solid. That was dissolved in water. And there's our two half reactions. To balance them, we would just use multipliers. That one gets multiplied by 2, and this one could be left alone or have a 1 put in front of it. That's a total balance problem. These were the steps I took to do it. This is the important information that you need to know. Batteries convert chemical energy to electrical energy. When they run out of chemicals, they run out of electricity. That's why batteries go dead. Basically, the anode and the cathode the anode gets fully used up, and then once there's no more anode, then the cathode can't gain mass anymore, and the electrons can't keep flowing, and so your battery dies. Rechargeable batteries actually reverse the charges on the anode and cathode and force this reaction to go backwards. This is where spontaneous and non-spontaneous comes in. That when the battery's operating as normal, we call it spontaneous. When you recharge a battery, if it is rechargeable, that would be the non-spontaneous reaction because you're forcing it to go backwards to recharge your battery. So that concludes this lesson on batteries. Voltaic cells, think of an easy way to remember voltaic cells. What are they? Batteries are rated in volts, like a 9-volt battery is that square one. So when you think voltaic, think batteries. That's an easy way to remember it. That's batteries in terms of the notes. We will be doing a couple more versions of this. We'll do electrolytic cells and a couple other things after this. But that concludes this video.